Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Energy is the ability of a body to do work. Its unit is either newtons meter or joule. Energy is scalar quantity, meaning that it has only magnitude. Here are different forms of energy. Kinetic energy is the energy possessed by a mass due to its movement. Its formula can be written as Ke equals half of mv squared, where Ke is the kinetic energy in joule, m is the mass in kilograms, v is the speed in meters per second. Gravitational potential energy is the energy stored in a mass due to its position in a gravitational field. Its formula can be written as GPE equals mgh, where GPE is the gravitational potential energy in joules, m is the mass in kilograms, g is the acceleration due to gravity equals 10 meters per second. H is the change in height in meters. Mechanical energy is the sum of the kinetic energy and potential energy of a system. Elastic potential energy is the energy stored in an object due to changes in its shape. Chemical potential energy is the energy stored within the chemical bonds between atoms or molecules. Electrical potential energy is the energy stored in the charges under an electrical field. Nuclear energy is the energy stored in the nucleus. Thermal, or heat, energy, also known as internal energy, is the energy refers to the energy contained within a system that is responsible for its temperature. Light is the radiant energy and is an electromagnetic radiation. Sound is the energy transferred through the vibration of the particles in matter. Conservation of energy. The principle of the conservation of energy states that the energy cannot be created and destroyed, but can only be transferred from one form to another. Efficiency is defined as the ratio of the useful energy output from the system to its total energy input. Efficiency can be expressed as the decimal, fraction, or percentage. Here are the efficiency value for different devices or bodies. Light bulb. The electrical energy input is 120 joules. The useful output energy is light of 50 joules. And the waste output energy is thermal of 70 joules. Therefore, the efficiency of light bulb is 50 divided by 120 is equal to 0.417, or 41.7%. Television. The electrical energy input is 550 joules. The useful output energy consists of 220 joules for light and 250 joules for sound. The waste output energy of 80 joules for thermal. Therefore, the efficiency of television is 470 divided by 550 is equal to 0.855 equals 85.5%. Electric motor. The electrical energy input is 750 joules. The useful output energy is 450 joules for kinetic energy. The waste output energy consists of 200 joules for sound and 100 joules for thermal energy. Therefore, the efficiency of electric motor is 450 divided by 750 is equal to 0.6 equals 60%. Running person. The chemical potential energy input is 800 joules. The useful output energy is 500 joules for kinetic energy. The waste output energy is 300 joules for thermal energy. Therefore, the efficiency is 500 divided by 800 is equal to 0.625, or 62.5%. Sankey diagrams can be used to represent energy transfers. These diagrams are characterized by the splitting arrows that show the proportions of the energy transfers taking place. The different parts of the arrow in a Sankey diagram represent the different energy transfers. The width of each arrow is proportional to the amount of energy being transferred. The left-hand side of the arrow represents the energy transferred into the system. The straight arrow pointing to the right represents the useful energy output. The arrow that bends away represents the wasted energy. This is a result of the conservation of energy, where the total energy input is equal to the total energy output, which is the sum of the useful energy output and wasted energy output. Therefore, the length of L1 equals L2 plus L3 plus L4. For example, let's draw a Sankey diagram for the electric motor with the electrical energy input is 1000 joules. The energy output as kinetic energy of 600 joules, thermal energy of 300 joules, and sound energy of 100 joules. We will set up the scale, where one division represents 100 joules. The width of the energy input arrow will be 10 divisions, equivalent to 1000 joules. The width of the straight arrow pointing to right, representing the useful energy output for kinetic energy, will be 6 divisions, equivalent to 600 joules. The width of the arrow that bends away, representing the thermal energy, will be 3 divisions, equivalent to 300 joules. The width of the arrow that bends away, representing the sound energy, will be 1 division, equivalent to 100 joules. To calculate the efficiency of the motor, we divide 600 by 1000 equals 0.6, or 60% efficiency. Thermal energy transfer. If there is a difference in temperature between two objects, causing thermal energy transfer from the hotter object to the colder one, this will continue until both objects are at the same temperature. We say that they are in thermal equilibrium. Thermal energy can be transferred from the hot object to colder object by conduction, convection, and radiation. Conduction. Conduction occurs mainly in solids. Particles in liquids and gases are much more free to move around than in solids, which is why they usually transfer energy by convection instead of conduction. At the hot end of the solid bar, the atoms of particles gain kinetic energy and vibrate faster. The atoms in a solid are close together, and so they collide with neighboring atoms, which in turn start to vibrate faster. In this way, heat energy is transferred from the hot end to the cold end of the solid bar. If a solid bar is the metals, which have free-moving electrons, this causes thermal energy transfer by conduction faster. This is because free electrons gain kinetic energy at the hot end of the bar. These free electrons pass on their kinetic energy through collisions with other electrons and metal atoms as they randomly diffuse through the metal. In this way, thermal energy is conducted from the hot end of the bar to the cold end. Good conductors are the substance that can transfer heat energy easily because they have free-moving electrons. Good conductors are mainly the metal, such as silver, copper, iron, aluminum, brass, and others. Poor conductors are called insulators, which are the substance that transfers heat energy difficultly, because they have no free-moving electrons. Insulators are mainly non-metal, except for graphite, which is a conductor. An experiment to distinguish between good and bad thermal conductors. Metals are better conductors of heat than non-metals. However, some metals are much better conductors than others. In this investigation, the thermal conductivity of 4 metals is compared, and the metals can then be placed in order from the best conductor of heat to the poorest. Set up the apparatus as shown in the diagram. For metals, rod are used to be iron, copper, brass, and aluminum. Attach a drawing pin to the end of each rod with a small blob of Vaseline. The ends of the rods, without the drawing pins, should be brought together so that they can be heated equally. Heat the ends of the rods equally with a blue Bunsen flame. Record the time taken for each rod to lose its drawing pin. When the temperatures of the far ends reach the melting point of wax, the pins drop off. The pin on copper falls first, showing it is the best conductor, followed by aluminum, brass, and then iron. An experiment to show that water is a poor conductor of heat. Set up the apparatus as shown in the diagram. Ice is trapped at the bottom of the boiling tube with a piece of metal gauze. When the water at the top of the boiling tube is heated strongly, it boils. The ice at the bottom of the tube does not melt. This shows that water is a poor conductor of heat. However, if the ice is allowed to float normally, it melts quickly when the water is heated at the bottom of the test tube. This is because the water molecules can move, so the water heats by convection. Water, like other liquids and non-metal solids, is a poor conductor of heat energy because its molecules do not have free-moving electrons to easily pass on their kinetic energy to their neighbors. So the heat can only be transmitted through the vibration of the particles. Gases are very poor conductors of heat energy because their molecules are very far apart, so kinetic energy cannot be transmitted from one molecule to another. Convection. Convection is the transfer of heat energy by the movement of currents within a fluid, which are liquids and gases, where the particles are free to move around. This is because the density of the fluid changes when it is heated. An experiment to demonstrate convection in water. A few crystals of potassium permanganate are placed at the bottom of a beaker of water. They dissolve and color the water near them purple. When the water is heated, the purple water rises above the Bunsen flame, moves across and then falls at the other side of the beaker before returning to the flame to be heated again. This movement of water is called a convection current. The reason why warm water rises. This is because the water is heated, its molecules gain kinetic energy and move around faster. They move further apart, and so the density of the water decreases. The warm, less dense, water rises as the water begins to cool. Warm water rises and pushes the cooler water over. The cooler water sinks. This is because the molecules of cooler water have less kinetic energy. They move closer together, and so the density of the water increases. The cooler, more dense, water sinks. When the warm water rises, then cooler, denser water moves across to take its place. This process continues until the water is heated evenly throughout. An experiment to demonstrate convection in air. Set up the apparatus as shown in the diagram. Place a lighted candle below one of the glass tubes. Hold a smoking paper above the other glass tube. The air above the candle flame gets hot and rises. Cooler air is then drawn from the other tube to replace the hot air. Smoke is used so that we can see how the air moves. The movement of hot and cold air set up convection current. The hot air rises. This is because the air above the candle is heated, its molecules gain kinetic energy and expands. The expanded air is less dense than the surrounding air and rise out of chimney. The cooler air sinks. This is because the molecules of cooler air have less kinetic energy, and so they are closer together. This causes the density of cooler air to be more than the hot air. Since the cooler air is denser, it sinks into chimney. Material that have trapped air in them such as cotton wool or bubble warp are good indicators, because air does not conduct heat, and trapped air cannot convection heat either. Radiation. Radiation is the transfer of thermal energy from one place to another by means of electromagnetic waves. Radiation can occur in a vacuum, particles of matter are not involved. Radiation is emitted by all bodies above absolute zero and consists mostly of infrared radiation. As an object gets hotter, it will also emit more thermal radiation. Thermal equilibrium. As an object absorbs thermal radiation, it will become hotter. If the rate at which an object emits energy is less than the rate at which it absorbs energy, then the object will heat up. If the rate at which an object absorbs energy is less than the rate at which it emits energy, then the object will cool down. Both processes will always move towards thermal equilibrium. Eventually, the object will reach a point of constant temperature where the rate at which it absorbs radiation is equal to the rate at which it emits radiation. At this point, the object will be in thermal equilibrium. Emitters and absorbers of thermal radiation. Matte or dull black surfaces of the objects are good emitters and good absorbers of thermal radiation. Shiny white or silver surfaces of the objects are good reflectors, but worst absorbers of thermal radiation. There are two factors which affect the rate at which energy is radiated from the surface of a hot object. The temperature of the surface. A hotter surface radiates energy at a greater rate. The surface area. Energy is radiated at a greater rate from a bigger surface area. An experiment to distinguish between good and bad emitters of infrared radiation. Set up the experiment as shown. The metal cube has its vertical sides painted with 4 different surfaces: matte black, white, shiny black, and silver. Fills the cube with boiling water. Leave for 1 minute to enable the surfaces to heat up to the temperature of the water. Use the infrared detector to measure the intensity of infrared temperature from each surface, or the temperature of the surface. Make sure that the detector is the same distance from each surface for each reading to ensure that this is a fair test. The results show that the highest temperature at the matte surface and lowest temperature at the silver surface. Therefore, matte surfaces are the best emitters of the thermal radiation. Silver surfaces are the worst emitters of thermal radiation. Another experiment to investigate the emitters of thermal radiation. Set up the experiment as shown. One can has a matte black surface, and the other can has a white surface. Fill the 2 cans with hot water. Use thermometer to measure the temperatures. Record and compare the results. Make sure that the initial temperatures of water in both cans are the same. Same time interval is used to record the temperatures. This ensures for a fair test. Matte black can has higher drop in temperature than white can at the same interval. This shows that the matte black surface is good emitter. An experiment to distinguish between good and bad absorbers of infrared radiation. Set up the experiment as shown. 2 metal surfaces are painted with matte black and white. They placed at a same distance from the heater to ensure that this is a fair test. 2 similar thermometers are attached at the back of 2 surfaces. The initial readings are taken on the 2 thermometers. The radiant heater is switched on and the temperature on the 2 thermometers recorded after 1 minute. The temperature at matte black surface is higher than at white surface after 1 minute. Therefore, the matte black surfaces are the best absorbers of thermal radiation. White surfaces are the worst absorbers of heat radiation. Another experiment to investigate the emitters of thermal radiation. Set up the experiment as shown. One can has a matte black surface, and the other can has a white surface. Place them at a same distance from the heater to ensure that this is a fair test. Fill the 2 cans with cold water at the same initial temperature to ensure that this is a fair test. Use thermometer to measure the temperatures at same time interval to ensure that it is a fair test. Record and compare the results. Heating the room by convection using the heater. When a heater is turned on, the air around it is heated. This causes the air to become less dense than the surrounding air, and warm air rises. As the air begins to cool, warm air rises and pushes the cool air over. Warm air displaces cooler air. So, the cooler air, denser, and air sinks. Cool air flows across to take the place by the rising of the heated air. This process continues until the warm air is heated evenly throughout the room. The same process happens when a room is cooled by an air conditioner. The air conditioner cools the air, making it denser than the surrounding warmer air. The cooler air sinks. Cool air displaces warmer air. The warmer, denser, air rises. Warm air flows to take the place by the sinking, cooled air. This process continues until the room is cooled evenly. Sea breezes. During the day, the sun's infrared radiation heats the land more than the sea. This causes the air above the land to become warmer and less dense than the air above the sea. The warm air above the land rises, creating a low-pressure area. Cooler air from above the sea, more dense, and sinks, creating a high-pressure area. Cooler air above the sea then flows in to fill the low-pressure area. This convection current causes a sea breeze to blow from the sea to the land. Land breezes. Land breezes is the reverse process with sea breezes. During the night, the land cools off more quickly than the sea. This causes the air above the land to become cooler and denser than the air above the sea. The cooler air above the land sink, creating a high-pressure area. Warmer air from above the sea, less dense, and rises to create a low-pressure area. The cooler air from above the land then flows in to fill the low-pressure area. This convection current causes a land breeze to blow from the land to the sea. The condition, convection and radiation of a fire burning wood. The woods are burned by a fire, as shown. Heat energy is transferred through a solid to the hand by conduction. Heat energy is transferred through air to hands at the side of a fire by radiation. Heat energy is transferred through air to the hands above a fire by convection, because warm air above a fire rises. This is because warm air is less dense than the surrounding air. Vacuum flask. The stopper is made of an insulator, such as plastic, rubber, or other materials, which reduces heat energy loss by conduction. The stopper also stops heat loss by convection and evaporation. The gap contains no air. So, there are no particles to pass on the heat energy by conduction or convection. The silvered surfaces reflect infrared radiation and reduce heat energy loss by radiation. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Work done is the product of force and distance moved in the direction of the force. Its unit is either newtons meter or joules. Work is the scalar quantity, which has only magnitude. The equation for work done can be written as W equals F multiplied by D, where W represents the work done in joules, F is force in newtons, and D is the distance moved in the direction of force in meters. For example, a force of 5 newtons acts on a box, causing it moves in the direction of force for a distance of 10 meters. Therefore, work done is 5 times 10 is equal to 50 joules. On the other, if a force of 5 newtons acts in the opposite direction of the distance moved, which is negative direction, therefore, work done is minus 5 times 10 equals minus 50 joules. When the person is walking of 10 meters and holding the box with weight of 10 newtons. A person walks 10 meters while holding a box weighing 10 newtons, the person exerts a force of 10 newtons to hold the box, but the box moves forward in a direction perpendicular to the force. Therefore, the work done by the person holding the box is 0. In another scenario, if a person with a weight of 600 newtons walks up a stairs with a height of 5 meters and a horizontal length of 6 meters. Therefore, the work done by the person is 600 times 5 is equal to 3000 joules. This is because the weight of the person and the height of the site of the stairs are parallel. In a case of a package with weight of W moving along a conveyor belt driven by a motor as shown. Therefore, the work done on the package is W times H. This is because the weight of the package is parallel to the height h. A 300 newtons force is applied to a box to move it up a ramp, as shown. Therefore, the work is done by the force when moving the box from x to y is 300 times 5, is equal to 1,500 joules. This is because the force of 300 newtons is parallel to 5 meters. Work done and the energy principle state that mechanical or electrical work done is equal to the energy transferred. We can express this relationship with the equation W equals F D equals delta E, where W represents the work done in joules, F represents the force in newtons, D represents the distance moved in meters, delta E represents the energy transferred. For example, let's consider a mass of 5 kilograms with an initial speed 2 meters per second. It is continuously exerted to a force of 10 newtons for 5 meters on a smooth surface. We need to find the final speed, v, at 5 meters. The work done by the force of 10 newtons is transferred to the kinetic energy, without any thermal losses due to friction since the surface is smooth. Therefore, the work done is equal to the increase in kinetic energy. The work done by the force of 10 newtons is 10 times 5. The increase in kinetic energy is half of 5 times v squared, minus half of 5 times 2 squared. Solving these equations, we find that the final speed, v, is 4.9 meters per second. In another scenario, let's the same box with an initial speed of 2 meters per second. It is exerted to a force of 10 newtons along a rough surface for a distance of d meters. As a result, 5 joules of thermal energy is lost, and the final speed is 5 meters per second. We need to find the distance moved by the box. The work done by the force of 10 newtons is transferred to both kinetic energy and thermal energy. So, we have the equation 10 times d equals half of 5 times 5 squared, minus half of 5 times 2 squared plus 5. Solving this equation, we find that the distance moved, d, by the box is 5.75 meters. In another scenario, let's consider a box with a mass of 5 kilograms being lifted from the ground to a higher level with a height of 3 meters. The weight of the box is 5 times 10 is equal to 50 newtons. The work done by the weight of the box is given by its weight multiplied by the height. Its result is 50 times 3 is equal to 150 joules. The gravitational potential energy increases by mgh equals 5 times 10 times 3. Its results is 150 joules. Therefore, the work done by the weight of the box is equal to the increasing in gravitational potential energy. The principle of the conservation of energy states that the energy cannot be created and destroyed, but can only be transferred from one form to another. For example, let's consider a mass of 1.5 kilograms that is dropped from rest to the ground from a height of 5 meters, neglecting air resistance. At the initial position, the mass has zero kinetic energy due to its zero speed. While gravitational potential energy is maximized at the greatest height. The maximum gravitational potential energy is mgh equals 1.5 times 10 times 5 is equal to 75 joules. The total mechanical energy of the system is the sum of its kinetic energy and gravitational potential energy, which in this case is 75 joules. It remains constant at any positions. As the mass moves downward, its height decreases, leading to a decrease in gravitational potential energy. This gravitational potential energy is transferred to kinetic energy, causing the speed to increase. When the mass reaches the ground with a speed, v, its gravitational potential energy becomes zero since the height is zero. At this point, all gravitational potential energy have been transferred to kinetic energy. To find the speed, v, to at which it reaches the ground, we can apply the principle of conservation of energy. The decrease in gravitational potential energy is equal to the increase in kinetic energy. Using the equation mgh equals half of m times v squared, we can rearrange it to v equals square root of 2gh. Substituting the values in g equals 10 and h equals 5. Solving this equation, the speed, v, equals 10 meters per second. If air resistance is present, the speed, v, at which it reaches the ground will be less than 10 meters per second, because some energy is lost to thermal energy due to air resistance. In another scenario, let's assume mass being thrown upward through the air with an initial speed 10 meters per second. At the initial position, the mass has zero gravitational potential energy due to its zero height from the ground, while kinetic energy is maximized at the greatest speed. The maximum kinetic energy is half of 1.5 times 10 squared equals 75 joules. As the mass moves upward, its speed decreases, leading to a decrease in kinetic energy. This kinetic energy is transferred to gravitational potential energy and thermal energy due to air resistance. When the mass reaches the maximum height, its speed is zero, leading to the kinetic energy is zero. And all of the kinetic energy is transferred to gravitational potential energy and thermal energy due to air resistance. To find the maximum height that the mass reaches, we can apply the principle of conservation of energy, assuming a thermal energy loss of 15 joules due to air resistance. The decrease in kinetic energy is equal to the increase in both gravitational potential energy and thermal energy. Using the equation half of m times v squared equals m, g, h, plus thermal energy lost, we can substitute the values in m equals 1.5, v equals 10, g equals 10, and thermal energy lost equals 15. Solving this equation, we find that the height, h, equals 4 meters. If air resistance is ignored, the height at which it reaches from the ground will be greater than 4 meters, because there will be no thermal energy lost due to air resistance. In another scenario, let's consider a pendulum with a mass of 0.6 kilograms being oscillated at rest from A to point B, and then to point C, neglecting air resistance. The total mechanical energy of the system remains constant at any position due to the principal conservation of energy. At point A, the initial kinetic energy is zero due to zero speed, while the gravitational potential energy is maximized due to the greatest height. As the pendulum swings from point A to point B, its height decreases, resulting in a decrease in gravitational potential energy. This energy is transferred to kinetic energy, causing an increase in speed. At point B, the kinetic energy and speed is maximized, while the gravitational potential energy is minimized due to the lowest point of the swing. As the pendulum swings from point B to point C, its speed decreases from the maximum to zero, leading to a decrease in kinetic energy to zero. This kinetic energy is transferred to gravitational potential energy. To find the maximum speed, v, that the mass reaches at the point B, we can apply the principle of conservation of energy. Assuming a decrease in height from point A to point B of 0.1 meters, the decrease in gravitational potential energy is equal to the increase in kinetic energy. Using the equation mgh equals half of mv squared, we can substitute the values in m equals 0.6, g equals 10, and h equals 0.1. Solving this equation, we find that the speed, v, equals 1.4 meters per second. If air resistance is present, the speed at which it reaches the point B will be less than 1.4 meters per second, because some energy is lost to thermal energy due to air resistance. In another scenario, let's consider a ball with a mass of 1.5 kilograms rolling downward at rest from a height of 2 meters to a height of 0.5 meters along the given path as shown. We assume there are thermal energy losses due to friction of 5 joules at the final speed v. To find the final speed v, we can apply the principle of conservation of energy. The decrease in gravitational potential energy is equal to the increase in both kinetic energy and thermal energy. Using the equation mgh equals half of mv squared plus thermal energy lost, we can substitute the values in m equals 1.5, g equals 10, h equals 2, minus 0.5, and thermal energy lost equals 5. Solving this equation, we find that the speed, v, equals 4.8 meters per second. If air resistance and friction is ignored, the speed, v, will be greater than 4.8 meters per second, because there will be no thermal energy lost due to air resistance. Power. Power is defined as the work done, or energy transferred per unit time. Its unit is measured in joules per second, or watt, W. Power is the scalar quantity, representing only magnitude. The equation of power can be expressed as P equals W divided by T, or E divided by T, where P is the power in watts, W is the work done in joules, T is the time in seconds, and E is the energy in joules. Experiment to investigate your power output. First, measure your mass using a scale balance, and then multiply by gravity to get your weight in newtons. Second, measure the height of one step of the stairs in meters. Third, count the number of steps. So, the total height of stairs equals n/d meters. Fourth, time how long to climb the stairs is seconds using a stopwatch. Work done climbing the stairs equals force times distance. Force is your weight and distance is the height of stairs. So, work done is W times N times D. Power equals work done over time taken. So, power is W, N, T, over T. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Energy resources are large stores of energy that can be used to generate electricity and heat homes and businesses. Some electricity drawn from the national grid is generated from non-renewable resources, and some is generated from renewable resources. Non-renewable energy resources are natural resources that cannot be replaced by nature as quickly as they are being used. Example of non-renewable energy resources include fossil fuels such as coal, oil, and natural gas. These fuels contain chemical potential energy derived from the sun. Nuclear fuel, such as uranium and plutonium, contain nuclear energy. Renewable energy resources are nature resources that can be repeatedly and dose not run out, because it can be replaced by nature at faster rate than they are being used. Example of renewable energy resources include biofuel or biomass is the waste of living things, which contains chemical potential energy derived from the sun during photosynthesis. Some biomass, such as wood from trees, food corp residues, and animal waste. Geothermal energy is the thermal energy found beneath the Earth's surface. Wind energy, which contains the kinetic energy derived from the sun. Hydroelectric energy, which contains the gravitational potential energy derived from the sun. Tidal energy, which contains the gravitational potential energy created by the moon. Wave energy, which contains the kinetic energy derived from the sun. Solar energy is light energy from the sun. Fossil fuel power plant. Fossil fuels such as coal, oil, and natural gas are burned to boil water, producing steam. This changes the chemical potential energy in fossil fuels to thermal energy, which is stored in the steam. The high-pressure steam passes through turbines and forces them to spin. This changes the thermal energy to kinetic energy, which is stored in the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This changes kinetic energy to electrical energy. This electrical energy is transferred through the national grid to homes or industrial factories. The water steam that passed through the turbines is sent to cooling towers and returns to the boiler again. Here are some of the advantages of fossil fuel power plants. Reliable energy resource. Fossil fuel power plant can produce electricity at any time, regardless of the weather. Produces large amounts of energy at fairly short notice. Fossil fuel power plants can produce large amounts of electricity quickly, which is helpful during times of peak demand. Scalable. Fossil fuel power plants can be scaled up or down to meet changing energy demands. Here are some of the disadvantages of the fossil fuel power plants. Non-renewable energy resource. Fossil fuels are a finite resource that will eventually run out. Produces air pollution. Fossil fuel power plants emit harmful pollutants into the air, which can contribute to climate change or greenhouse effect and other environmental problems. The cost of fuels affects the price of electricity. The price of fossil fuels can fluctuate, which can affect the price of electricity generated by fossil fuel power plants. Nuclear power plant. The nuclear fuels such as uranium or plutonium in the nuclear reactor will releases the thermal energy due to nuclear fission. This converts nuclear energy to the thermal energy. This thermal energy used to boil the water, producing steam. So the thermal is stored in the steam. The high-pressure steam passed through the turbines and forces them to spin. This converts the thermal energy to kinetic energy, which is stored in the turbines. The turbines are connected to a generator, which causes the generator to spin and producing electrical energy. This converts kinetic energy to electrical energy. This electrical energy is transferred through the national grid to homes or industrial factories. The water steam that passed through the turbines is sent to cooling condenser and returns to the boiler again. Here are some of the advantages of nuclear fuel power plants. Reliable energy resource. Nuclear fuel power plant can produce electricity at any time, regardless of the weather. Large amount of energy is produced from a small amount of fuel. Scalable. Nuclear fuel power plants can be scaled up or down to meet changing energy demands. No greenhouse gas emissions. Nuclear power plants do not produce greenhouse gases or other pollutants. Here are some of the disadvantages of the nuclear fuel power plants. Non-renewable resource. Nuclear fuels are a finite resource that will eventually run out. Waste disposal. Nuclear waste is radioactive and must be disposed of carefully, which can be a high costly and difficult process. High cost to build. Nuclear power plants are very expensive to build, which can make them a less attractive option than other forms of energy. Safety concerns. Nuclear power plants pose a risk of accidents, which can have catastrophic consequences. Biofuel or biomass power plant. Biomass, such as woods or corpse residues, are burned to boil water, producing steam. This converts chemical potential energy of biomass into thermal energy, which is stored in the steam. The high-pressure steam passes through turbines and forces them to spin. This converts the thermal energy to kinetic energy, which is then stored in the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This converts kinetic energy to electrical energy. This electrical energy is transferred through the national grid to homes or industrial factories. The water steam that passed through the turbines is sent to cooling condenser and returns to the boiler again. Here are some of the advantages of biomass power plants. Renewable energy resources. biomass are an infinite resource that will never run out. Less garbage in landfills. Biomass power plants can help to reduce the amount of garbage that goes into landfills. Carbon neutral. Biomass is carbon neutral, meaning that the carbon dioxide produced when the fuel is burned is balanced by the carbon dioxide absorbed when the biomass is grown. Here are some of the disadvantages of the nuclear fuel power plants. Can take a lot of land. Biomass power plants can require a lot of land to grow crops or harvest wood. Not entirely clean. Biomass power plants can still produce some emissions, such as nitrogen oxides and sulfur dioxide. Geothermal power plant. Water is pumped into shafts below the Earth's surface. Water is heated by the hot rocks and returned via another shafts as steam. The thermal energy is transferred from the earth to the water steam. The high-pressure steam passes through turbines and forces them to spin. This converts the thermal energy to kinetic energy, which is stored in the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This converts kinetic energy to electrical energy. This electrical energy is transferred through the national grid to homes or industrial factories. The water steam that passed through the turbines is sent to cooling towers and returns to the Earth's surface again. Here are some of the advantages of geothermal power plants. Renewable energy resources. Geothermal energy is an infinite resource that will never run out. Reliable energy resource. Geothermal power plants can produce electricity at any time, regardless of the weather. Here are some of the disadvantages of the geothermal power plants. Few suitable locations. Geothermal power plants can only be built in areas where there is hot rocks lie quite near to the surface. This is possible in volcanic areas. High cost to build. Geothermal power plants are very expensive to build. Can result in the release greenhouse gases from underground. Waves power plants. High-speed waves pass through the chamber wall and compressing air column. This transfers the kinetic energy of the waves to the air particles. The air particles pass through the turbines, forcing them to spin. This transfers the kinetic energy of the air particles to the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This converts the kinetic energy to electrical energy. This electrical energy is then transferred through the national grid to homes or businesses. Here are some of the advantages of waves power plants. Renewable energy resources. Waves energy is an infinite resource that will never run out. No greenhouse gas emissions. Waves power plants do not produce greenhouse gases or other pollutants. Here are some of the disadvantages of the waves power plants. Few suitable locations. Waves power plants can only be built in areas where there is waves energy. Not reliable. Wave power is not always available, it depends on the weather. Waves are generated by wind, so if there is no wind, there will be no waves. Tidal power plants. Tides occur twice a day due to the gravitational attraction force between the Earth and the Moon. The water at high tide level flows to the low tide level. This converts the gravitational potential energy of the water into kinetic energy of the water. This high-speed water passes through turbines. This transfers the kinetic energy of the water to the kinetic energy of the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This converts the kinetic energy into electrical energy. This electrical energy is then transmitted through the national grid to homes or businesses. Here are some of the advantages of tidal power plants. Renewable energy resources. Tidal energy is an infinite resource that will never run out. No greenhouse gas emissions. Tidal power plants do not produce greenhouse gases or other pollutants. The tides are very predictable. the amount of energy can be produced at regular intervals. Here are some of the disadvantages of the tidal power plants. Few suitable locations. Tidal power plants can only be built in areas where there are strong tides, where the ocean is narrow and the coastline is indented. Not reliable. Tidal power is not always available. Environmental impact. Tidal power plants can have a negative impact on marine life, such as disrupting fish migration patterns and disrupt shipping. Hydroelectric power plants. The water is stored at a dam, and then it falls from the high level to the lower level. This converts the gravitational potential energy of the water into kinetic energy of the water. The high-speed water passes through turbines. This transfers the kinetic energy of the water to the kinetic energy of the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This converts the kinetic energy into electrical energy. This electrical energy is then transmitted through the national grid to homes or businesses. Here are some of the advantages of hydroelectric power plants. Renewable energy resources. Hydroelectric power is an infinite resource that will never run out. No greenhouse gas emissions. Hydroelectric power plants do not produce greenhouse gases or other pollutants. Reliable. Hydroelectric power plants can produce electricity at any time, regardless of the weather, and large amount of energy at short notice. Scalable. Hydroelectric power plants can be scaled up or down to meet changing energy demands. Here are some of the disadvantages of hydroelectric power plants. Few suitable locations. Hydroelectric power plant usually requires the flooding of valley by building a big dam. Environmental impacts. The construction of hydroelectric power plants can have a significant environmental impact, such as flooding and habitat destruction. Economic impacts. The construction of hydroelectric power plants can be expensive. Wind power plants. Strong wind passes through the turbines, forcing them to spin. The kinetic energy of air particles is transferred to the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This converts the kinetic energy to electrical energy. This electrical energy is then transmitted through the national grid to homes or businesses. Here are some of the advantages of wind power plants. Renewable energy resources. Wind power is an infinite resource that will never run out. No greenhouse gas emissions. Wind power plants do not produce greenhouse gases or other pollutants. Here are some of the disadvantages of the wind power plants. Few suitable locations. Wind power plants can only be built in areas where there are strong wind. Noise. Wind turbines can produce noise, which can be a nuisance for people who live nearby. Not reliable. Wind power is not always available, it depends on the weather due to wind speeds must be sufficient. Can have a visual impact. Solar power plants. Light energy shine on the solar cell, producing the electrical energy. This converts the light energy into electrical energy. The electrical energy is then transmitted through the national grid to homes or businesses. Here are some of the advantages of solar power plants. Renewable energy resources. Solar power is an infinite resource that will never run out. No greenhouse gas emissions. Solar power plants do not produce greenhouse gases or other pollutants. Here are some of the disadvantages of the solar power plants. Few suitable locations. Solar power plants can only be built in areas where there is strong sunlight. Large area needed to produce a large amount of the energy. Not reliable. Solar power is not always available, it depends on the weather, and only works when sunny. Solar panels. Solar panels can be used to heat water or air for heating in a house. Heated water for domestic use, such as showering, bathing, and washing dishes. Sunlight shines directly on the solar panels. A glass sheet is coated with a substance that reduces the reflection of sunlight. Glass sheet traps hot air. This air is heated by sunlight and then transfers that heat to the water in pipes by conduction. A blackened metal surface is a good absorber and conductor of heat. It collects sunlight and transfers it to heat, then heating the water in pipes by conduction. Copper pipes are good conductors. They collect sunlight and transfer that heat to the water in pipes by conduction. The insulating material reduces heat loss from the water in pipes. The heated water then flows through pipes to the rest of the house. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.